dear friends, it's my pleasure to introduce our today's speaker, Professor Kauffman from Chicago in Novosibirsk, and today he will tell us about the Dirac equation and the Majorana Dirac equation. It's supposed to be the last seminar in our series of seminars, so please welcome.
Thank you very much. I think I have a slideshow here somewhere. Just a moment. There it is. Oh, sorry. There, I think that will work, and can you see my pointer?
Yes.
Moving?
Yes, it's perfect.
Okay.
And we can see a pointer also, yes.
Good. All right. So this talk is about Myrana Fermions. I'll have to tell you what they are, and braiding, which you know, and the Dirac equation, which you may know. And much of the work toward the end is joint work with Peter Rowlands. I'll explain. There. Yeah. So Myrana is a physicist from the 1930s, Italian physicist, and he had a very interesting idea. There was the Dirac equation, and I will tell you about the Dirac equation later on, but the Dirac equation involves matrix coefficients in this equation, and the matrices often have complex numbers in them, so that the solutions to the Dirac equation, as it's usually designed, are almost always involve complex numbers in a non-trivial way. But it's possible to change the matrix algebra that informs this equation so that the matrices are entirely real matrices. And Majorana figured out a way to do this. And that meant that the equation, rewritten that way, could have real solutions that are equal to their own conjugates. And Majorana interpreted this as possibly corresponding to particles that were equivalent to their own antiparticles, and wondered whether perhaps such particles as a neutrino might be Majorana particles. And to this day, no one knows about that. But the notion of using the Majorana idea of particles that are equivalent to their own conjugate, that would be equivalent to their own antiparticle, occurs in condensed matter physics these days in relation to quantum computing. And so I'm going to be telling you a story about this, starting with some simple ideas and then eventually getting over to the Dirac equation, and in the middle, talking about braiding. So let's begin by talking about an extremely elementary particle. This particle P is going to have the property that it can interact with itself to annihilate itself. And star means it produced energy. Star acts as though it were the identity if you're thinking algebraically. And then I add an extra property to this particle that it can interact with itself to produce itself. Now, it turns out that that's a very nice mathematical particle. And it is conjectured to be descriptive of certain kinds of states for two-dimensional physics that have to do with the quantum Hall effect. So it's not entirely unreal, but on the other hand, it isn't entirely observed either. But it is something you can think about mathematically, and it's quite interesting, as you'll see. So that's our particle P. For a little while, we're going to be watching this particle P. Now, I have to tell you something about fermions. And if you look it up in a physics book, you'll see that in the quantum field theory end of things, fermions are described by operators which can create them or annihilate them. Was there a question? No. Okay. If there is a question, please let me know. I understand that sometimes a microphone will open up and close again, but I'm happy to answer any questions. So standard fermions have annihilation and creation operators, and these satisfy an algebra. It's a well-known algebra, and we'll look at some examples of it as we go along. One property of these operators is that they square to zero. They're nilpotent of order 2. And this corresponds to the Pauli exclusion principle that you can't have more than one fermion in the same state. And then there's an anti-commutation relation that happens, that f star plus f star f is equal to the identity. And I'm not going to try to motivate that right now. However, I want to talk about a little more algebra. So now I'm going to talk about another bit of algebra. And this bit of algebra is a Clifford algebra generated by A and B, little a and little b. And these square to 1, as elements generating elements in a Clifford algebra may do. And they anti-commute. AB is minus BA. So this is, to mathematicians, this is a very familiar kind of algebra like Grossman algebra. Except the squares of these are 1 rather than 0, but it's a relative of Grossman algebra. But here's a curious thing. It came to pass that physicists wanted to call particles that satisfied this algebra Majorana Fermions. And they weren't looking at Majorana's original equation when they were doing that. They were looking at something a little more elementary, which I'm going to show you on the next slide, and that's this. Suppose that you have A and B, which satisfy the Clifford algebra identities. And suppose we defined U to be A plus IB over 2. I is the square root of minus 1, and it commutes with everybody. And U star is A minus IB over 2. And now I claim that U and U star will now satisfy the Fermion algebra. So this is a little exercise that will make you feel familiar with the Fermion algebra if the Clifford algebra felt familiar to you. Can you do that in your head? Before I write it down, you can do it in your head. You see, U plus U star, what about that? Well, that's going to be A, right? U plus U star is A. So that's a nice fact you can see from this. On the other hand, what about squaring U? If you were to square U, you'd get A squared, but you have minus B squared. And A squared minus B squared is 0. And then on the imaginary score, you're going to have AB and you're going to have BA multiplied by I. But AB plus BA is 0. So U squared is 0. And U star squared is 0. And U plus U star is equal to A. And U plus U star squared is equal to A squared, which is 1. But what is U plus U star squared? Why, that's U squared plus U star squared, both 0, and U star plus U star U. And that was what we said. U star plus U star U equals 1. I wrote it down here. You see? You multiply U by itself, and it all cancels out. Similarly for U star. And you look at U star plus U star U, and that's the same as U plus U star squared, which is A squared, which is 1. So this leads to a curious speculation, which you might find a bit unbelievable that anybody would speculate on the face of such slim bits of non-commutative algebra. What's the speculation? U is supposed to be an electron, an ordinary fermion like that. U star would be the anti-electron. Could this say that the electron is composed of 2 other kinds of particles, each of which would be their own antiparticle? Could this say that the electron is composed of 2 Majorana particles? In what circumstances could you even imagine finding this? So that's very interesting. But people in condensed matter physics started to think about this a few years ago because they could do things with electrons that would let them do experiments along these lines. They can have electrons crowded in a very thin wire. And they can measure correlations between the ends of the wire. I will show you pages of some papers that refer to this, and we'll see it in a few minutes, how this works. And we're also going to see that there's a very interesting representation of the braid group that is related to these Clifford Algebra elements. So this is a very interesting bit of theoretical physics and whose speculations anyone can understand, but why you would believe such speculations is, of course, a long story. I want to talk about thinking about particles and their interactions. So I'm going to now be doing a little bit of iconics and drawings and scribblings and things like that. So for example, there's a logical system that I like due to G. Spencer Brown, and he uses a box. And his little box, or half box, interacts with itself in two ways. In one way, it's concentric, and it does itself in. It cancels. And in the other way, it's next to itself, and it condenses. So this is just like our particle P. His formal entity interacts by either interacting with itself to produce itself or annihilating itself. Interesting. That's a formalism that has some other significances, which I won't go into. But we could use a circle in the same way. And then we would have two circles are supposed to interact to produce a circle, or they should interact to produce nothing. And we could also write formally, and this is called fusion algebra, that the particle interacts with itself to produce star or P, where plus is thought of as an or. But you could also write it in that way and think about what would happen if you interacted with itself 3 times and so on. It's a useful bit of formalism. But as far as the interactions are concerned, you could start thinking of them as cobordisms if you wanted to, if you're inclined topologically, so that the two circles can interact to produce one circle by going through a saddle point, and two circles can interact to produce nothing by going through a saddle point and a minimum. Or if you like your critical points to be non-Morse, they could be concentric and get closer and closer and closer together, and finally go through a non-Morse critical level and disappear like that. So you can wonder what the geometric properties would be of a particle that had that form. And if you were to take the string iconics that I'm using here and flatten them, or you could think of them in 3-space and imagine braiding them, or you could turn them into little graphs and think of braiding them. But this flattening turns out to be remarkably important. You can flatten tubular cobordisms like this and turn them into double line kind of pictures like this. In fact, there's a relationship between surface cobordisms and temporally Lieb algebra that runs along this track. But then the particle itself would have to be indicated, and I've indicated it by a little box. And then the interaction of the two particles corresponds to the fact that I can bind these lines in such a way that 2 lines go in, 2 lines go out, and they can be added up, combined, recombined to form one going out. Or they can be combined like this so that nothing goes out. These are these 2 cases. And then we would have one last process, which you might imagine, which it goes into a 4-fold kind of particle, and that one would have to be forbidden. Now it turns out that this kind of framework actually has an underpinning which looks like this, that you can think of expanding that box into a temporally Lieb projector. This is not where I'm going in the talk. I just am digressing here. But you can expand that into a temporally Lieb projector, and then all of this becomes algebraically, diagrammatically meaningful, and you can evaluate using the Jones polynomial or the bracket. And you can obtain braid group representations that are dense in the unitary groups, and you can see that these Fibonacci particles should have a rich braid group unitary braid group representation associated with them. And this turns out to be related to the conservative physics at certain levels in it. So these iconics actually do work. How you would know, just on the basis of iconics, how to walk over into this, of course, I don't know. I would like to be able to tell a pure mathematical story with a bit of physics in it that would motivate going over to this kind of recoupling structure in braid group representations associated with the Jones polynomial. But in fact, the stories are more complicated, involving Chern-Simons theory that we know that suggests this. But getting back to the particle itself, I called it a Fibonacci particle on some earlier slide, and there's a reason for that. And this is a bit of elementary mathematics. We have that P interacting with P is either 1 or P, 1 plus P. So if you interact it one more time, you get P times 1 plus P times P, which is 1 plus 2P. And if you multiply again, you get 2 plus 3P. And if you multiply again, you get 3 plus 5P, and so on. And you get Fibonacci fractions of particles that are either the identity or the particle itself. And so Fibonacci numbers come up here, and vector spaces associated with these particles have Fibonacci dimensions. I think I've already said what's on this slide, so we'll just skip it. And I don't really need this slide either. But you can imagine particle interactions that are string-like, that behave in the way that we're talking about. And you can wonder whether you could construct some very elementary physics of a science fiction or mathematical nature that would hold all the things that I've said, including the recoupling theory and the Jones polynomial part. The kind of physics that that is based on is a good deal more complicated and involves a lot of conjectural jumps that people have made to get to these models. This is a nice magazine illustration of these ideas from a Scientific American article about these things. The little whirlpools in the base correspond to vortices in a two-dimensional physical situation. And the braiding, of course, is the particles moving around in time and accumulating into a braid. Or it is the human controller keeping these particles moving in the way he wants. Now I want to talk about fermion algebra from an elementary point of view also. And this is an extremely elementary point of view. What I'm going to do is I'm going to think of a little oscillator that oscillates between 0 and 1. And these could be Boolean values for all I care. I'm not using very much mathematics, just 0 and 1. And I have two ordered pairs here, 0, 1 and 1, 0. And I'm going to add them and multiply them termwise. So this is earlier than matrix multiplication. This is the termwise multiplication of ordered pairs, and otherwise added termwise as well. And I think of these as kind of conjugates of one another. And now, what do we know? Well, we know that P times Q is 0, and we know that P plus Q is 1, 1, which is 1. We know that P squared is equal to P and that Q squared is equal to Q. So we have a little algebra here of this. But then I also want to think of these as each capturing a little bit the temporality of the oscillation. And so I'm going to do that by adding another operator to the situation, which, when you apply it on either side of a 0, 1, turns into a 1, 0. In other words, the 0, 1 combined with that operator is the same as that operator times the 1, 0. And that operator squared is equal to 1. It's a little time-shifting operator if you think of this process as going along in time. And then I form U and U dagger, which are time-sensitive oscillations. And notice what happens with them. Let's square U. We get P eta times P eta, but eta P eta is Q. PQ is 0. And your dagger squared is Q eta Q eta, which is QP, which is 0. And U plus U dagger, by definition, is P plus Q times eta, just eta, because P plus Q is 1. And so you get U dagger plus U dagger, U equals 1. There's the Fermion algebra occurring in the most elementary way I can make it occur mathematically, right? From a little oscillation. This has to do with wondering what do these algebras do and how simply can you represent them. Now I can get to the square root of -1 and the Clifford algebra in a similar way, as long as I allow my underlying arithmetic to have -1 and +1 in it, as well as just 0 and 1. And it's the same story. I'm going to have eta, so that AB eta is eta BA. Eta AB is equal to BA. Eta AB eta is BA. That's the time-shifting operator, the permutation operator. And if I let I be equal to 1 comma -1 times eta, then you'll see that I squared is -1. We've got I. But we also have a Clifford algebra. We've actually constructed a Clifford algebra. Here's the Clifford algebra. E is 1 minus 1. E squared is 1, 1, which is 1. Remember, we multiplied it term by term itself, like a diagonal matrix. E eta, on the other hand, is going to be 1 minus 1 eta, which is -1, 1. I should have shifted the eta over to the other side, and I didn't. That eta belongs on the other side. Too bad. That's minus E eta. E eta is minus E eta. Or E eta, eta E eta is minus E. E squared is 1, eta squared is 1, and E eta is minus eta E. There's the little Clifford algebra right there, okay? So the Clifford algebra comes up very easily, very elementary way out of thinking about some very basic thing. There's another way of thinking about this. I should have made a slide for it, but it will come up later, so we'll leave it at that. This way of thinking about oscillations and temporality giving rise to algebra, if you generalize it a little bit, it gives rise to all of matrix algebra. Just one more way to motivate matrix algebra. One of the reasons for thinking about this has to do with looking at the way matrix algebra occurs in elementary physics. It occurs in mysterious ways which you would like to understand better. Consider this matrix here. This is, again, a digression, but if you haven't seen this, you should see this. This is a really beautiful point. This matrix is Hermitian. Conjugate complex numbers across the diagonal, real numbers on the diagonal, and it represents a point in space-time, t, x, y, z, take its determinant in your head, would you please? You get t squared minus x squared minus y squared minus z squared. You get the signature of space-time, 1 minus minus minus, in this way of looking at it. And that means that since the determinant is preserved by conjugating it by appropriate things, you can think of the Lorentz group in relation to the structure of this Hermitian matrix. So somehow a lot of physics is condensing into the patterns of elementary matrix structure. It makes you want to think about it more. So now I want to go over to the speculation that I was telling you before. I have a row of n electrons, and I'm going to think of it as 2n Majorana Fermions, and show you what it looks like when you look at some people's papers. Now, I said recent work, but this has been around for quite a while. Recent to me means 1965, I suppose. But this is really recent, 2000. Kitaev wrote a paper in which he worked out what the physics would be like if you looked at physical structure, rows and pairs of Majorana Fermions in the sense that we've talked about. So each of these is an electron, but it's really a row of 2n Majorana Fermions, and you look at the correlations between the ends of these chains, in the quantum measurements. And Ivanov, around the same time, started thinking, and this I'm going to show you something about, what would the braiding be like for Majorana Fermions? What if you took a couple of Majoranas of the kind that I'm talking about here and moved them around one another? How would they braid? And other people, more recently, this is 2012, and there are more recent ones than that, are writing papers about the dynamical detection of Majorana Fermions in current bias nanowires. You see what I said before. You have electrons in nanowires. They kind of pair up. They're going to share their Majorana Fermions. In the end Majorana Fermions will be correlated in some way that you might measure. And there is some controversy about whether the experiments have really measured it or not, even now. But this is current research. And you see, these are diagrams from papers using exactly the formalisms I've been playing with here today. And thinking about the properties of the nanowire and all that. I want to show you the braiding. So of course, here's the braiding. This is the basic braiding identity. And if I am looking for a representation of the braid group, then I'm going to want this identity to be satisfied. And this is what Ivanov did in his paper. He did it this way. This is quite remarkable. I hope this isn't unreadable. He said, suppose I have a row of Majorana Fermions, a collection of them, just a mathematical collection of them, A1, A2, A3, A4, A2n. They anti-commute. Any pair of them anti-commute, all right? But we put them in an ordered row. And they square to 1, or every one squares to 1, and they all anti-commute, okay? That's all. It's very simple algebra. Now we're going to define an operator, S of I, and it's going to be 1 plus AI plus 1 times AI and divided by root 2. And you'll check that its inverse is 1 minus AI plus 1 times AI divided by square root of 2. Now, just as when I multiplied two Clifford Algebra elements and got a square root of minus 1, remember EA squared was minus 1? This squares to minus 1. So this looks like a square root of minus 1, but it's part of a non-commutative system of things. And then you can verify that these operators satisfy the braiding relations and that they commute when they're far apart. And Ivanov didn't actually use that representation of the braid group. He stepped across it and defined an action of his operators on Majorana Fermions themselves, because he's thinking of these mathematical bits as particles, which are sitting down there in a plane. And he would conjugate the x particle by the ith operators. So you would have SI, X, SI inverse. And then you calculate, using this setup, you calculate that the ith particle is exchanged to the I plus first one, and the I plus first one is exchanged to minus the ith one. They interchanged, and all the others are left fixed by the ith operator. And it's easy to see that that's a representation of the braid group. So you get a representation of the braid group happening on this row of Majorana Fermions. The check that my representation that I told you about satisfies the braid group identity is quite amusing. So we might look at it. You see, I said that I had a product of two things, AI plus 1 AI, and that would be a square root of minus 1. But these two that you're multiplying, the ones that are adjacent to one another, you can check that they anti-commute. So let's go back one step for a moment. This one and the very next one will anti-commute. I leave it to you to check. So then the abstract form of it is you have two anti-commuting guys, they square to minus 1, and you put them in this form, sigma A, sigma B, and now you want to see that they're braiding. And you can check easily enough from what I wrote here that ABA equals B and BAB equals A. Yeah, a little bit of algebra. And then you say sigma A, sigma B, sigma A, and you multiply it out. Do a little work. I can't I shouldn't run through this in front of you, but I'm pointing out to you that can be done on a half a piece of paper. You check the calculation, and you end up with something that's symmetric in A and B. Well, then that means that sigma B, sigma A, sigma B is the same thing. And so we have a representation of the braid group here. Algebraically, a little mysterious. And there's the general theorem about braiding in the Clifford algebra that I mentioned. And here's a special case. The special case is when you started with only 3 of these Majorana elements, these Clifford elements, then you can form BA, CB, and AC. And those satisfy the quaternions. So here's the quaternions arising naturally in this situation. And then these operators in the quaternions satisfy the braiding. So the quaternions are intimately related to a representation of the braid group, a fact that should be paid attention to by topologists, I think. So as I said, what Ivanov did was he conjugated in this way to get an action on the space of Majorana fermions by the braid group. And his action looks like this, that if you braid 2 of these, if you move one around the other, then what happens is that they interchange, that T of X is Y and T of Y is minus X. So the braiding is like an interchange. And this is related to the belt trick, which I've drawn because it's hard to illustrate the belt trick over the internet. But if you have a belt between your hands, and maybe we should illustrate it. Let's see how close we can come to illustrating it. The problem is I'm not sure how much you will see. I have a belt between my 2 hands, and there's no twist in the belt. Presumably no twist in the belt, like that, right? And then these 2 particles, they interchange position. And I don't twist them, I just interchange their position. And then we look at the belt and we find that the belt has acquired a 360-degree twist as a result of interchanging the position. So that connection is related to the way SU2 double covers the rotation group in 3 space. That's the belt trick. But what you don't get out of the belt trick is the notion that that minus sign that the 360-degree twist corresponds to, you do not get that that minus sign ought to be associated with one of the particles and not the other particle. That requires some further structure. And that's the structure we just went through, that if you have each of these with that Clifford algebra in back of it, and the Clifford algebra interactions in back of that, then this same braiding actually assigns a sign to one of the particles and not to the other. And so we get an algebraic representation of the n-strand braid group. And that one is unitary, very simple but unitary. And people imagine using it to do computations if they could only control these fermions, which would not be easy. So that's the braiding part of this. That's very intriguing. And next, we want to talk about the Dirac equation. So I want to be self-contained here. What did Dirac do? How did he invent an equation that went beyond Schrodinger's equation? Well, he's trying to make it relativistic. He wants a relativistic equation. He wants it to fit with special relativity. And in special relativity, there's a remarkable relation, which I should have thrown a derivation into the slideshow, but you may have seen it before. And that says that E squared equals P squared plus M squared. It's really a relative of E equals MC squared. And P is momentum and M is mass, rest mass. And the speed of light has been set equal to 1 for convenience here. Otherwise, there'd be some C squareds and things in there. Well, but this presented a problem for Dirac because you see, when you're writing down a quantum mechanical equation, you want to relate energy to momentum and mass. You want to write down a Hamiltonian. You want to write down the energy expression. But it would seem here that you needed to take the square root of the sum of the squares of P and M. And that would make the equation nonlinear, and it could wreak havoc with how you would deal with this. So Dirac had the idea of linearizing it by trying to write the E as a sum of operators, non-commuting matrices, in other words, times P and M. Now, if you just tried it, E is alpha P plus beta M, and squared the E, then you see you would get alpha squared P squared plus beta squared M squared plus PM times alpha beta plus beta alpha. We're not assuming they commute. And that tells you what to do if you're trying to do this. It tells you you should take alpha squared equals 1, beta squared equals 1, and alpha beta plus beta alpha equals 0. In other words, alpha and beta should be that same Clifford algebra that we were looking at before, or some appropriate matrix representation of that Clifford algebra. The Clifford algebra is down at the bottom of things, talking to the Pythagorean theorem. There's some missing mathematics here, I'm sure, right? It looks like this should have come along with the Pythagorean theorem a long time ago, but it didn't. It comes along recently. And so now Dirac knows what to do. He says, okay, I'm going to define my energy operator to be equal to alpha times the momentum operator plus beta times the mass, which is taken to be the mass operator. And the energy operator in quantum mechanics is I d by dt. This I will not try to tell you about in this talk. And the momentum operator is minus I d by dx. There is a long story, very interesting story, going back to Schrodinger, which explained that you could use differential operators for momentum and energy and write the differential equations by decoding physical expressions into differential operators. And this is the code. So for us, this is the code. So then you see I d by d psi dt, that represents I energy operator applied to psi, equals minus d by dx alpha applied to psi, that's momentum applied to psi, and beta m applied to psi. So this is a differential equation, and that is Dirac's equation in one space variable and one time variable. So the Dirac operator is the difference here, I d by dt plus I alpha d by dx minus beta m. And the Dirac equation can be written as this operator applied to psi equals 0. And of course, you need to put it into x, y, z as well, but we'll get there. That's the Dirac equation, a very clever idea. And then he calculated things with it and found out that it was giving good results. And so it became part of canonical physics. And it also has problems associated with it, and all that became part of canonical physics. So I want to show you a kind of mathematical experiment, which goes back to my friend Peter Rowlands. Let's apply O to, in this algebraic form, without making matrices out of these yet. Let's apply it to a plane wave. A plane wave is e to the I times momentum times x minus energy times time. That's scalar momentum, scalar energy, not the momentum operator. We apply the differential operator to it. Well, you know, this is really the reason why those things decode the way they do. If you take I d by dt and apply it to this, you see that energy comes out as an eigenvalue. And if you take minus I d by dx, you see that momentum comes out as an eigenvalue. So if you apply O to this, you get E minus alpha P minus beta M times psi. You get a Clifford algebra factor multiplying the psi. Okay, fine. Let's call it delta. So here is Rowlands' remarkable observation, very simple observation. Multiply that delta by beta alpha. Let's do it. We get E beta alpha. We get alpha, beta alpha, but that's equal to beta minus alpha alpha, and alpha squared is 1, so this is beta p. Alpha went away. And here we have beta times beta alpha, and that's just going to be minus alpha. And I lost a sign, too bad. All right. But you see, U now is nilpotent because this guy squares to minus 1, as we've seen a number of times. You take the two Clifford algebras and you multiply them together and it squares to minus 1. This squares to 1, that squares to 1. So, and they all anti-commute. This anti-commutes with that and that and that and that. So you just get the coefficient squared, and minus e squared plus b squared plus m squared equals 0. Aha. So if you were to take the operator and multiply it by beta alpha, you could rewrite the differential equation in such a way that this would be a solution. In other words, I'm saying that U psi is a solution to the Dirac equation. Now let me do it again and then you'll see what I'm saying again. I'm sorry, I think this takes 2 looks. Here's the energy operator, here's the momentum operator. This is the equation really. This is what happens when you apply it to psi, and this is what happens when you apply the momentum operator to psi. And we take this to be the operator, E hat minus alpha p beta m, and we define D to be equal to that operator times beta alpha. So I change the operator a little bit. It becomes beta alpha E hat plus beta P hat minus alpha M. And now we have a new Dirac operator, D, and D psi gives me beta alpha E gives me U psi. So D psi is U psi. Now I've done the work and we can relax a little bit. D psi is U psi, but U squared is equal to 0. So if you apply D to U psi, you get 0. D applied to U times E psi is U squared times that, which is 0. So that tells you how to build certain elementary solutions to the Dirac equation. They're of the form on nilpotent U multiplied by the plane wave psi. And so you see things are actually coming together in this elementary point about fermions. The U squares to 0 and acts just like a fermion operator. And so we're picking up algebraic, Clifford algebraic versions of fermion operators, which represent fermions. You can think of the fermion that solves this as corresponding to the operator itself. And if you were to take an antiparticle, you would reverse the time. It would change a sign in here, and you would get a U dagger or a U star. And then you will have the fermion algebra, unnormalized in this case. So we can get the fermion algebra and we can get fermions by this observation about how to get fermions corresponding to plane waves in the Dirac equation. Now let me skip forward a little bit. Of course, you can do this in full 3 dimensions, and you have to modify the algebra a little bit. I'm going to skip exactly how you modify that algebra and go to the 3-dimensional version for Myrana. So I'm going to use the Clifford algebra we started with, and this is what I could have said earlier. The E, the epsilon, is a diagonal matrix, minus 1, 1. The eta is a permutation matrix, 1, 1. And then these satisfy exactly what I was saying. E squared is 1, eta squared is 1, E eta is minus eta E. And now we want to write down a Dirac equation in 3 dimensions that only uses real matrices. Well, what we're going to do is we're going to take E and eta and another copy, E hat and eta hat, independent and commuting with these. you can think that when I write down E eta or E hat, eta hat, that I'm taking a tensor product of matrices. That's what I'm actually doing, but I won't worry you about that. I'll just write it algebraically. So now what do I want? I want the Dirac algebra to be satisfied, and I find that I can put in coefficients, in this case eta hat eta and epsilon hat eta and the other one, and get a Dirac equation involving only real matrices. And this is indeed what Majorana did. But of course, if you look in his paper, there are a lot of big 4x4 matrices doing the work. I'm writing it in abstract algebra. And then this is the guy whose solutions we'd like to understand. So this part of the project that Peter and I embarked on was, why not use this nilpotent idea to see if we can write down some basic solutions to the Majorana Dirac equation? Well, that's what I want to show you. So I'm not going into the details of why this is satisfying the right algebra, partly because I can show you later something simpler about it, and partly because it's just the method that I want to show you. So here's the method, you see? Here's the D. This is the particular D I was just showing you. Here's the psi, where that, of course, means a 3-vector, x, y, z, right, and the momentum components. And then we apply D to psi, and we pull out a Clifford Algebra element, a little more complicated than the one we had before, but it's the same idea. Here's E, and here are Px, Py, and Pz multiplied by some Clifford things, and some i's come down because of this. Even though this is a real equation, I'm applying the operator to a complex exponential. Well, but you know how to do this. This is what you do in elementary differential equations. If you can write down a complex solution to a real differential operator, then you can take the real part and the complex part and get real solutions. So that's what I want to do. But I want to get solutions. Is it going to be giving me a nilpotent solution? Because those are the ones that I like. Well, the answer is yes. This expression here, if I multiply it by eta epsilon, turns into a nilpotent, and that means that it's the same as before, that I can write the solutions in terms of u times psi. And the u is ia plus b, where ab is minus ba. They're gleaned from here. They're purely real Clifford elements, and b squared is minus m squared and a squared is minus m squared. So you see, it's a Majorana algebra like the one we started with. And the fermion is getting decomposed into 2 Majorana pieces, just as we had before. Only now it's actually happening in relation to Majorana's equation. And this is new, even though you might think, well, they must have known that way back when Majorana was doing this, that they associated the Majorana operators to solutions to Majorana's equation. But it's not so. It didn't happen in that order. And so that means that we can write down solutions to Majorana's equation, and even explicit ones. You see, if omega is the argument in the plane wave, then we're going to take those Majorana elements times cosines and sines, and we will have solutions to the Majorana Dirac equation, real solutions. And what we can do with them, we don't know yet. But that's where we are. But I want to show you a little bit further about where we are, and then we can come to a stop. So I want to tell you a little story. Feynman, in his book with Feynman and written by Feynman and Hibbs, gave an exercise about the Dirac equation. It's something that I got involved in as a piece of research a long time ago, earlier than this project. And it has to do with the following idea. Here is space and here is time, one dimension of each. And that means that the speed of light is 1. So a particle going at the speed of light coming out of the origin could be zipping right along the side of this rectangle. or it could be going in the negative direction and going along this side of the rectangle. And Feynman said, you should think about particles which are zittering back and forth, going at the speed of light, and then going at the speed of light in the other direction, and then going at the speed of light. In terms of space, they're going back and forth at the speed of light. Jump forward, speed of light, jump back, speed of light, going like that, like a little random walk. And starting here and going through that zittering and ending up wherever you wanted to end up. Maybe you wanted to end up here at that point in space-time. So you should think of trajectories like that, and you should add them up. And you should add them up taking I to the number of corners in the trajectory. And then you'll get a solution to the Dirac equation, he said. And you're supposed to do this exercise. Well, this was one of those good exercises, and it spawned a lot of papers, including one that I wrote with Pierre Noyes in the 90s. But quite a number of papers. We did a nice job in our paper, which I can't tell you all about. But I'm going to tell you about how it relates to what we're doing today. Feynman's idea is you count the number of corners and add up over the paths, and you can get solutions to the 1 + 1 Dirac equation. And the key to it is working in light cone coordinates, t plus x and t minus x. That gives you these coordinates rather than t and x, the coordinates of the path that are naturally associated with going right and left along the paths, like that. And when you rewrite the Dirac equation that way, and you do it for Majorana, there's no I. Feynman's thing becomes -1 to the n, number of corners. And the Dirac equation becomes two functions, a left and a right psi, such that the derivative of one of them with respect to r is equal to the other, and the derivative of the other one with respect to L is equal to minus the first one. That turns into the Dirac equation. And it was out of that and discretizing that one could see that the checkerboard sums would satisfy this equation. That was Feynman's exercise. And Feynman's exercise is intimately related with this version of the Dirac equation. How does that relate to what we were just talking about? Let's look. Here we are in 1 + 1 dimension, doing a special case. And here's our operator. I assure you, this is the right Majorana operator for this. And here is my algebra. I have epsilon, I have eta, and I have epsilon eta, all real. That squares to -1, right? And then we get a nilpotent, and again, we have to go into the complex numbers at that point to get the nilpotent. We multiply by I eta. And then we get a nilpotent, and we get the A's and the B's that satisfy what I showed you before. With a squared equal m squared and b squared equals m squared. And everything is working nicely in that abstract way that I showed you. And I go and I get the real solutions and I write them down. Okay? There they are. And now I want to change coordinates into the light cone coordinates. R is t plus x, L is t minus x. And you see what that does to my plane wave term. It gives me a minus e minus p minus e plus pl. And then those things that I told you will actually satisfy a standard Dirac equation. And we end up in the end with this. Here we are. After going through our machinery, we end up with this little trigonometric gadget. Psi1 is minus m sine of this guy. And psi2 is e plus p cosine of that guy. E squared equals p squared plus m squared. We're now at the point of doing elementary exercises. I assert that psi1 and psi2 satisfy these linked differential equations. You can see it easily. Take d psi1 dl. You're going to pull out an e plus p, but the e plus p is multiplying this one, and the sine is turning into a cosine. So indeed, and there's a minus sign there. So you got m psi2. And now what about taking the derivative of psi2 with respect to r? Well, then you get an e minus p, but e minus p times e plus p is e squared minus p squared, which is m squared. And it picks up and goes back over to the other one. So you see the relativistic equation is intimately working with the coefficients in here. and we end up with a solution to this nice Feynman checkerboard version of the Dirac equation. This presents me with an interesting problem, which I've been working on now for a few days, but I don't have a good answer to it. This one does not get described directly in terms of the checkerboard the way we were doing it before, but it's very simple in trigonometric. And it has its own combinatorial description as paths in relation to the checkerboard that I'm beginning to understand. So it's giving a new point of view about the checkerboard. And you see that the kind of formalism that we're working with isn't just up in the air. You can take that abstract algebra and focus it and go into actual solutions that can be compared with other things. So it's a lot of fun. One last bit and I'll stop. This is an abstraction that helps for understanding the form of the Dirac equation. I'm going to call a Clifford algebra a space-time algebra, and this may be similar to what you would find in a book on entitled Space-Time Algebra by Hestinus, but it's not exactly the same. If the squares of the first three are 1 and the square of the last one is -1, Minkowski space-time signature, and they all anti-commute. So these are Clifford algebra. And I'll call that a space-time algebra. So this guy squares to -1, these square to +1, and they all anti-commute. Well, then, if you're trying to write the Dirac equation, you can say immediately after analyzing it that this is the story. You need this operator, E1, E2, E3, and E4. This one squares to -1, these square to +1, 1 on the d by dt. That's the Dirac operator. All right. So then you can use this to try to explore which operators will be Majorana operators. How do you get real solutions to this? And like the one I showed you. For example, the one I showed you, now you can see it. I have E1 as eta hat eta, E2 is epsilon, E3 is epsilon hat eta, and E4 is this product. And this guy squares to 1. This guy squares to 1, that guy squares to 1. But this guy, because he's got a product of 2 of these, squares to -1. And they all anti-commute. And it's a little combinatorial exercise to try combining these symbols of this kind to see which ones will combine to produce Majorana-type solutions. And there's a number of them, and you can figure out exactly what they are. And this is what the answer looks like, where I now switched to 2 algebras, lowercase ij plus ji equals 0, uppercase ij plus ji equals 0, everybody squares to 1. And then these basic triples actually generate all of the possible space-time algebras that are real. If you look at one of these, you'll see this is the guy that squares to -1. This guy squares to -1, that guy squares to -1. This has 2 guys that square to -1 multiplying each other, and so it squares to +1. And you see, you go through a bit of combinatorial enumeration and you can find them all. And now what the physical significance is of these different algebras that all fit into what Majorana wanted, we don't know yet, but we're working on it. And that's where we are. And that's my report. It goes across a lot of different things, from sort of nitty-gritty combinatorics, like I've been telling you here, to representations of the braid group and things that start impinging on condensed matter physics, and various exercises that are somewhere between mathematics and physics. So I think it's a very interesting project, and we're in the middle of it still. I'll stop there.
Okay, thank you very much. Very interesting. So, questions, please. Maybe okay, I see something interesting in the chat.
Can I ask?
Please.
Thank you for interesting talk. I have two questions. First one, you constructed some representations of braid group. Can you say something about the kernel of this representation? Is it true that
Oh,
it's
yes.
playful?
Yes, certainly. The representation that I was showing you, all the braiding operators have order 8. They're all of the form, if you think of an I in there, 1 plus I divided by the square root of 2. So they're order 8. They're non-commuting square roots of -1, so it's more complicated than just I. But every generator has order 8. So I don't know that I've characterized the kernel, but it's got a big kernel.
You construct in first representation on some finite group. The image of braid group is finite. Is it
That's
correct?
That's correct.
Okay. Thank you. And the second question, if you have solution, if you have some representation of braid group, B3, for example, you can construct solution for the Young-Baxter equation. And if we have solution for the Young-Baxter equation, we can define some algebraic system with two algebraic operations. Sometimes it's Quandl, sometimes Rec, sometimes Dirac. What is algebraic system we can construct in using your representation?
Right. In the case of the Myrana Fermion representation, you can take a 4x4 piece of it that satisfies the Yang-Baxter equation.
Yes.
And you could use, it's unitary, so it can be used as a generator for quantum transformations. That's why it's of interest for topological quantum computing. But you had a different notion you were going to do. What was it that you wanted to do? You wanted to do something. I heard you, but I didn't quite catch it. That you wanted to do with the Yang-Baxter solution.
But is it possible to construct Dirac using your representations?
To construct what?
Dirac or Quandl. See, you have a solution for the Young-Baxter equation. It's a pair. We have map S, which send the pair AB to some other pair. And we can define two binary operation on our algebraic system.
Well, it's not. I mean, yeah, you could probably get an associated biquandle to it, if that's what you had in mind. I haven't thought about what the biquandle would look like in relation to that. It's a very simple braid group representation. But I should go back to my slideshow for a moment to point out something. Sorry. There it is. This one is much more complicated. This one, I'm not talking about in this talk, but this one starts out with 2x2 matrices, R and FRF, that give a braid group representation for the 3-strand braid group that is dense in the unitary group U of 2, not at all finite, and quite complex. And then it extends outward to braid group representations that are dense in the unitary groups by tensoring. And these are more interesting mathematically, maybe, than the one that I was showing you that comes out of the Majorana Fermions. But the one that comes out of the Majorana Fermions is extremely simple, as I said. As a braid group representation, it's nothing more than changing a sign on interchange, or let's go back to what it looked like. Oh, there it is. You see, these are the operators that are generating it, and this is some square root of -1. So that has order 8. And so you're right to ask exactly what am I generating here. I should think about it, characterize what that group is. It's not finite.
In this case where sigma A and sigma B have finite order, is it correct?
What did you say about sigma A and sigma B?
Sigma A, they have finite orders.
Yes, they do. But they're each of order 8.
Ah, okay.
That's what I was saying. You see, A squared is -1. So this looks like 1 plus I over root 2. It has order 8.
Okay. Thank you.
Mm-hmm.
Lou, please have a look. There are 2 questions in chat. Can you see? If you go to the chat, you see.
In the chat, let's see.
Yes, there are 2 questions.
Can you say more, and in what sense expect Majorana can be helpful in quantum computing? Yeah, you said mathematicians. I'm not sure what mathematicians expect. A lot of physicists are speculating that they might be able to control the kind of physics that happens in nanowires and actually be able to have braiding happening. And then they would have systems where they could produce unitary transformations in physical reality that would generate quantum computing. The reason is that even a simple braiding operation like that is strong enough to generate quantum computing in the presence of some other operators. You don't need a lot. It's like ordinary computing is generated by a NOT gate. That's all you need, really, and a lot of wiring. And quantum computing is generated by the equivalent of a NOT gate, and these kind of things are like NOT gates, plus not just wiring, but some local symmetries, local unitary symmetries. And what people hope is that the topological kind of structures would be more impervious to perturbation than other structures. Because a topological structure is, by its definition, able to be the same even though you perturb the system in one way or another. So that's the hope. But I think that hope will be a long time being realized in the case of the Majorana Fermions as I've described them. They're too delicate to be easily observed. So I wouldn't get my hopes up if I were you on that score. Iterand algebra, what I've called Iterand algebra is what I was showing you, using ordered pairs or ordered n tuples plus groups acting on them to do the algebra. And I don't know that it has anything in particular to do with vertex operator algebras. But I wouldn't be surprised to see some of those kinds of patterns in vertex operator algebras.
Thank you. Are there more questions, comments? If no, let us thank the speaker again. Thank you very much. So it was the last talk in our virtual conference, and I hope maybe next year we'll meet all together, not just in internet, but say in the ordinary life. And thank you very much for Lou and to other speakers. So we close our session. So thank you very much.
Yes, thank you very much. It's been a pleasure to be working in this conference. We had so many remarkable talks spanning topology and many applications. It's really a wonderful and worthwhile conference. Thank you all.
And of course, all slides can be found at the homepage of the conference. We have all video and all slides. Thank you very much, everybody.